Okay, just to check. This one is also visible, right? All right. So we discussed a bit of parity and all. So today we'll start something called uh, identical particles. I guess all of you have gone through the last two units, right? Have you? Have all of you gone through the last two units of the booklet given by IGNU? Am I audible?
ସାର୍ ଏଗ୍ରିମେଣ୍ଟ
Yes,
ବୁକ୍
sir.
କେବେ ବି ଆଭେଲେବଲ୍ ହେଇନି ଆମ ପାଖରେ।
ନାଇଁ ବହିଟା ଅଛି ମାନେ ଯୋଉ
Soft
ପିଡିଏଫ,
copy is available.
ହଁ ପିଡିଏଫ ଟା ଅଛି ତ?
Yes, sir.
ଆଜ୍ଞା PDF
ହଁ,
ଅଛି ହଁ।
ହଁ। ସେ ଫାର୍ଷ୍ଟ ଦିଟା ୟୁନିଟ୍ ପଢିଛନ୍ତି ତ ସମସ୍ତେ?
ସେଟା ଗୋଟେ ୟୁନିଟ୍ ପଢିଥିଲୁ, ଆଉ ଗୋଟେ ୟୁନିଟ୍ ପଢିନି।
Okay, so it is important, because
Okay, okay.
we will be developing on those two units, unit third. Huh? So this is basically about identical particles. Let me, before starting the real stuff, let me give a very crude example. Uh, so let's say we are dealing with only one particle. Classical mechanics, most of the classical mechanics when we studied in plus two and all, it was only one particle system most of the time. So then it is like, even though there are many particles, we are focusing our attention to only one particle. When we start thinking about more than one particle, like two, three, four, two particle system already you have solved in quantum mechanics 1, hydrogen atom. Hydrogen atom has already been discussed in quantum mechanics 1. This course is quantum mechanics 2, right? So in quantum mechanics 1, uh, hydrogen atom has already been discussed or not?
Not discussion.
Okay, so then it will be discussed. Okay, uh, because the Schrodinger equation you solve initially, that is for only single particle. So px square by 2m plus bx, which is the Hamiltonian, right? But when you start looking at proton and electron, or two particle system, helium atom, then you actually start uh, thinking about more than one particle. So the natural question that comes into mind is, are those two particles, let's say we are talking about helium atom. Let's take a very simple example. Hydrogen atom you will be solving, where you have one core of proton, and then an electron is revolving around it. So it is a Coulombic potential. Okay, but what happens when you have helium one? So, or a hydrogen molecule. Let's say you take H2. So then there are two protons and then there are two new electrons. So if we start thinking about more than one particle, then the natural question that comes into mind, whether those two particles are distinguishable or not. uh, it is I don't know whether that is acceptable or not, but see, for example, we Indians, uh, among ourselves, we can easily distinguish, right, from the face. But when you go outside India, looking at our structure, like skin color and face shape, others can judge, okay, these are Indians. Okay. So similarly, so if we look at a bunch of particles, can we distinguish them, or all of them look same to us? That is the fundamental question. Because if, let's say, we have two particles and both of the particles are same in all respect, then we cannot distinguish them. Uh, but if we can, in classical mechanics, most of the time we consider them to be distinguishable, and if not, if they're identical, still we can try to track its trajectory. If we have two identical masses of mass m, still if they are colliding, all of you have must have done this collision problem in plus two level, that two masses of mass m1 and m2 moving with speed v1 and v2 collide, and what happens after the collision, what will be their speeds and positions after collision. In all those cases we actually thought about identical particles, but still we are able to track their trajectory, whereas in quantum mechanics it is not possible. But if we know them for sure that this is particle 1, this is particle 2, that means we know their position, then we cannot track their trajectory independently if they are identical. That's the problem with quantum mechanics. That's why, if you come to page number 73 on the PDF, it says that in general, n particle system n greater than 2, for example, the quantum mechanical problem for any atom heavier than hydrogen cannot be reduced to an independent single particle problem. What is even more surprising is that the quantum mechanical problem of two particle system is much more complex when the two particles are identical in all respects. This we have to mark these words. So when the two particles are identical in all respect, yes, in quantum mechanics all electrons are identical, right? So all protons all are identical. So how exactly we'll deal with the quantum mechanical problem of electrons, protons, or for any other particles of such kind? So then we'll try to develop a mathematics. First, we'll try to see what happens for a distinguishable particle in classical mechanics. Then, what happens to indistinguishable or identical particles in classical mechanics. And then we'll take over what happens to identical particles in quantum mechanics. Okay? So, let me just highlight what can we expect from this unit is a Schrodinger equation for a system of two distinguishable, we can distinguishable non-interacting particles. I'll come to that. When the system can be described in terms of normal modes. So what does that mean? That means we have two particles which are distinguishable. We can distinguish particle 1 and we can distinguish particle 2, and they are not interacting. So that means the potential of one is not affecting the potential of the other. So they can be summed algebraically. So that means V x1 x2 is that basically V x1 plus V x2. So this signifies that they are non-interacting particles. So there is no potential between x1 and x2. Whereas, if you come to the third point, is general solution of Schrodinger equation for a system of two distinguishable but interacting particles. Interacting particles, when particles are interacting, then that is potential of one is affecting the potential of the other, then it will be Vx1 x2 will be equal to Vx1 minus x2 in the center of the mass or reduced coordinate system. And then later on we'll move over to quantum mechanics and then see how exactly in quantum mechanics, in quantum state, identical particles are dealt with. A system of n degrees of freedom, system with n degrees of freedom. So suppose now we want to describe quantum mechanically a classical system. So, we want to describe quantum mechanically a classical system with n degrees of freedom, for which the n Cartesian coordinates. So if it has n degrees of freedom, so it will have n Cartesian coordinates. For example, if we have 3 degrees of freedom, then we express it in I cap, j cap, k cap, right? X, y, z. So if a system, classical system, has n degrees of freedom, and so then it can be expressed by n Cartesian coordinates starting from x1 to xn, and the corresponding momenta are p1 to pn. We extend the quantum mechanical description of single particle with one dynamical degrees of freedom. So this problem is like if it is we have n particles with 1 degree, each one of them having 1 degree of freedom, or we have one particle having n degrees of freedom. So there is a set of n mutually commuting position operators x1 to xn with the condition that they are mutually commuting. Xi cap xj cap commutator is equal to 0. What does this mean? This means xi xj minus xj xi is equal to 0. So that means if you operate I cap and then operate j cap, it's same as you operate j cap and then you operate I cap, like that kind of. So mutually exclusive. Mutually orthogonal. So one will not depend on the other. X1 cap will not depend on x2 cap. X2 cap will not depend on x3 cap, like that. So if we have a quantum classical system with n degrees of freedom, so then n Cartesian coordinates are x1 to xn and momenta are p1 to pn. With the condition, so in quantum mechanics, how is that we will describe? We will describe them by operators x1 cap to xn cap, and with the condition that xi xj cap commutator is equal to 0. That means they are mutually commute. There is simultaneous eigen basis for these commuting operators, which we can call coordinate basis of the system. So already we discussed about basis. Basis is nothing but a set of vectors describe mutually independent vectors, orthogonal vectors, which will describe the whole system, right? So now, if we have n degrees of freedom, the state will be described by x1, x2 up to xn. Try to relate in normal day-to-day life that if we want to describe a three-dimensional problem, what exactly will describe a position or something like that, a momentum, anything, I cap, j cap, k cap. So we need I cap, j cap, k cap. So similarly, if we have n n Cartesian coordinates, so then we need x1, x2 up to xn. So all these will form the basis system. So the eigencat will be involving all from x1 to xn, right? So if I operate xi cap, which is the position operator on the state, it will give me the value xi, the position of the particle, right? The eigenbasis is normalized. That means what? If I take the bracket x1 prime, x2 prime up to xn prime with x1, x2 up to xn, it will be delta x1 minus x1 prime, x2 minus x2 prime, like that. So this is the condition, right? So that this condition is basically signifying that they are these x1, x2 up to xn are mutually orthogonal. The wave function corresponding to the state psi will be, we're just writing, this is the way we write, right? So x1, x2, xn operating on psi is basically nothing but psi x1, x2 up to xn. So psi, which is the wave function, will have all the basis vectors x1, x2 up to xn. So probability of locating the particle between x1 and x1 plus dx1. So this is more related to the probability density. So what is the probability that we'll find the particle between x1 and x1 plus dx1, x2 plus dx2, xn plus dxn will be just psi mod square dx1 dx2. So this is the volume element. This is the volume element dx1 dx2 dx3 up to dxn. At this point, I just want to ask you one question. These things are already being taught in quantum 1, is it? Are you familiar with these kind of notations or not?
Yes, sir.
Yes. Okay, that's good. So then
Yes, sir.
yeah. So normal bracket notation, huh?
Yes, sir.
Okay. So the momentum operator corresponding to ith degree of freedom will just be pi will be minus ih cross del by del xi, right? And if we know in classical mechanics, if we have an observable, then it will be represented by an operator in quantum mechanics, right? And then if we have the system where we are dealing with position and momentum, so then the observable can be expressed in terms of position and momentum. So any dynamical variable of the system which depends on xi and pi is represented by an operator. So this is very much from quantum one, that any dynamical variable or the observable which of the system that can be expressed in terms of an operator, and that operator O cap is nothing but a function of xi and pi.
It's A and PA.
Yeah.
That's it.
And we have the following. I mean, this is obvious that this is stating that the position and momentum are canonical. That means xi, xj commutator and pi, pj commutator are zero, but xi, pj, pi, xi, pj commutator is ih cross delta ij. So this is also nothing but telling you that we cannot. I mean. We can have this system of basis vectors where x1, x2, x3 up to xn are mutually orthogonal, and similarly pi, p1, p1, p2, p up to pn are also mutually orthogonal. All right. If h cap is the Hamiltonian of the system, then the time evolution of the observable is nothing but ih cross del o cap by del t is equal to uh, the commutator of O with H. In particular, if we want to have the position, then it is xi with H commutator, and if we are interested in knowing the momentum, time evolution of the momentum, then it will be the commutator of pi with H. So it is important that if we have the position or the momentum, or for that matter any observable at a particular time, then from these two relations 3.1i and 3.1j, we can find their value at in future or after some time t. So this is kind of the time evolution of the observable. So this is very important. I think this will be used many places. So this is something you should keep in mind. IH cross del O cap by del t, which is the time evolution of the operator O, is nothing but the commutator bracket of O with H. There is a classical correspondence also in classical mechanics. We'll deal with that. So next we come to a two particle system. We come to two particle system. Uh, so let me read out a couple of sentences, then we try to understand. Uh, we first consider a system of two distinguishable particles. This is important. First, two distinguishable particles, which we label as 1 and 2. So that means the particles can be distinguished. The masses of the two particles, M1 and M2, and they are located at R1 and R2. So these are two particles having two different masses at two different positions. So we can clearly distinguish them. The state vector of the system is psi, and we generalize our idea of a function psi x, y, z as psi r. Huh? So psi r will nothing but what will it be? So if we have two particles and we want to express the two particles using one wave function, so that will be psi r1 r2, right? That will be psi r1 r2, which is nothing but
Vector quantity.
psi x1 y1 z1 and x2 y2 z2, which is like the two positions, right? And we can also, in bracket notation, we can write r1 r2 ket vector. That is fine. It's just a representation. So the wave function psi r1 r2 time dependent one, psi r1 r2 t, is defined as follows. How? The joint probability of finding the particle 1 in the volume dqr1 and the particle 2 in the volume dqr2 is nothing but psi mod square dqr1 dqr2. This is just coming from what we have discussed here, 3.1f. So what is the probability of locating the particle? Is basically psi mod square dx1 dx2 dxn. So here also we are doing the same thing, dx1 dx2 dx1 dy1 dz1, that makes dqr1, and dx2 dy2 dz2, that makes dq r2, right? So in a normalized condition, this must be equal to 1, right? The wave function is normalized. The total probability of finding those two particles in the whole space should be 1 unity, right? To simplify this discussion, we can represent it with, so psi x1 x2, if we write it in one dimension, psi x1 x2, we can write it in like x1 x2 bra with psi cat as a representation. So what will be the position? X1. So x1 cap operating on x1 x2 will give me x1 value. X1 cap operating on x1 x2 state will give me the position x1. So similarly, x2 cap operating on x1 x2 cat will also give me the x2 value, the position. So the joint probability of finding the particle 1 between x1 and x1 plus dx1 and particle 2 between x2 and x2 plus dx2 is psi mod square dx1 and dx2. What exactly we are doing here? Where we have two particles. Initially, particle 1 is at x1, particle 2 is at x2. Now we are interested in finding quantum mechanically what will be the probability of finding those two particles. So particle 1 will be where? At x1. So the probability, we have to take the window x1 plus dx1, x1 and x1 plus dx1. Similarly, particle 2 at x2 and x2 plus dx2. So then the volume would be, here it is dx1, here it is dx2. So total volume dx1 into dx2, psi mod square dx1 dx2. So the normalized condition would be psi mod square dx1 dx2 integration would be equal to 1, right? The position and momentum again. So xi pj will be equal to ih cross delta ij. Xi xj will be equal to 0 and pi pj equal to 0. Following from the previous discussion. And time evolution, how exactly will be the time evolution? So ih cross del psi by del t will be equal to H psi. Are all of you familiar with this one? 3.5a Schrodinger equation, time evolution, right?
Yes, sir.
Yeah. And for a two-particle system, we have the kinetic energy of the first one, h cross square p1 square by 2m1 plus h cross square p2 square by 2m2 plus the potential energy one. And at this point, we are not discussing what exactly is the nature of the potential. Okay. And how the how the state will evolve, the state psi t will evolve. So E is the E cat over here in equation 3.6, E cat is the eigenstate of H cap. H psi is equal to E psi. Yeah. H psi is equal to E psi is the time independent Schrodinger equation which you will be solving, right? H psi is equal to E psi. So where you take p square by 2m or minus h cross square by 2m. I don't know if how far has it been taught in quantum 1? So let me write it a little bit. So your h cap is nothing but p cap square by 2m plus v, right? So if you are taking in one dimension, 1D, it will be how much? In 1D it will be h cap would be px square by 2m plus px. Here it will be vr. Okay. So now for time independent, time independent Schrodinger equation. So what will it be? So px square by 2m plus bx psi x will be equal to E psi x. All of you familiar with this one, right?
Yes, sir.
Yeah. So this kind of reduces to minus h cross square by 2m d square by dx square in one dimension
Yes, sir.
psi of x will be equal to E psi of x, right? Now, if you look at here, so h cap is nothing but h cross square by 2m1 p1 square for first particle, h cross square by 2m2 p2 square for second particle, and then the potential energy. And how exactly the state varies? How exactly the state time evolution of the state? So it will psi t will be equal to exponential minus iet by h cross into the eigenstate of h cap, time independent one. So that's what it is saying, where E cat is the solution of the equation He is equal to E. So instead of, because we already have written psi, so it is kind of avoiding writing psi here. So H psi is equal to E psi, that kind of equation. Okay. So if we have, if we explicitly write, so then we will write minus h cross square by 2m1 del square by del x1 square plus minus h cross square by 2m2 del square by del x1 square and psi e x1 x2 v x1 x2 psi x1 x2 will be equal to e psi x1 x2. So psi e x1 x2, which is the energy eigenstate, is nothing but x1 x2 bra with e cat. Is it clear up to this point? All of you are following this equation 3.6b?
Yes, sir.
Yes, sir.
Okay. And then equation 3.7a is normal that we already have discussed for canonical commutation relation. Xi will be equal to IH cross delta Ij, and Xi xj Pi Pj commutators are 0. What happens if we have n instead of 2? If we have n particle system, it is telling instead of 2 particle, if we have n particle, so we'll extend it. So it instead of minus h square by 2m1 p1 square minus h square minus is taken common. So h square by 2m2 p2 square h square by p3 square by 2m3. So similar up to going up to h square by 2mn pn square. So this is the kinetic energy part, and then the potential energy part. So the potential energy part we have to see whether they are interacting, non-interacting, what exactly is the case. Okay. And the time evolution will be simply you solve for the time independent Schrodinger equation and get the eigenstate, which is psi e x1 up to xn, and exponential minus iet by h cross. So this part over here, e to the power minus iet by h cross, is the time dependent part, and this is the time independent part. So non-interacting, so we'll consider the first case of non-interacting particles, two particle system. In case of non-interacting, this Vx1 x2, which we discussed here, Vx1 x2 x3 up to xn. If it is two particle, then it is only x1 x2. So for two particle system, Vx1 x2 is equal to Vx1 plus Vx2. If that is the case, and we write the Hamiltonian, you can see h square by 2m1 p1 square plus h square by 2m2 p2 square plus vx1 plus vx2. So I can take this vx1 to this p1 square, so that it becomes h1 plus h2 Hamiltonian. So kinetic energy plus potential energy for the particle 1, kinetic energy and potential energy for particle 2. So then it will be h1 cap plus h2 cap, right?
H2.
And if we try to solve the time independent Schrodinger equation, how exactly we'll write? We'll write like this, right? So if this is the Hamiltonian, so it will be minus h square by 2m1 del square by del x1 square v1 vx1 operating on psi e x1 x2, because your psi you'll see in quantum 1 as well that
Parle ji.
in this kind of cases this
Na na.
psi x1 x2
Aage ache. Context. Mana.
would be equal to psi1 x1 into psi2 x2. Variable separation method in mathematical physics and BSc you must have done this.
Others, please mute yourself.
No.
It would be better if others can mute. And yeah, thank you. So this partial differential equation in two variables x1 x2 can be reduced to two ordinary differential equations by method of separation of variables. So if those of you who are not familiar, I would suggest you to go to mathematical physics book or mathematical physics, where variable solution of partial differential equation by variable separation method. Look into that part. So this will be much more clear. So at this point, I can only say that if your equation is written like this, that this is one variable operating on a function which is containing both x1 and x2. This is another variable and operating on the function which is again containing x1 x2, then we can actually write this x1 x2 psi x1 and x2 as psi1 x1 into psi2 x2, where psi1 explicitly depends on x1 and psi2 explicitly depends on x2. If that is the case, then this one equation can be written combination of two equations, because here it will be psi1 x1 psi2 x2, here also psi1 x1 psi2 x2, psi1 x1 psi2 x2. So if we separate it, variable separate it, we can simply write minus h cross square by 2m1 d square by dx1 square. Uh, you can notice. So here from del square, it has become d square. That means this psi one explicitly depends on x1. Here it was function of two variables x1 x2, but here it is function of only one variable. So minus s square by 2m1 d square by dx1 square plus dx1 psi 1 is equal to u1 psi 1. And similarly, minus s square by 2m2 d square by dx2 square plus vx2 psi 2 is equal to e2 psi 2, and u1 plus e2 is equal to e. So that way we can find out the solution independently. So this is the Schrodinger equation for particle 1 and the Schrodinger equation for particle 2, and the time evolution would be e to the power minus iet by h cross. So depending on what kind of potential the two particles have, if it is Coulombic, then it is the hydrogen atom like. I can understand that hydrogen atom has not been discussed yet, it seems. But once you hydrogen atom is nothing but that the potential, the Schrodinger equation potential would be k upon r square, right? What is the potential? Potential is k by r. Sorry, k by r, right? All of you following this one? What I'm talking?
Yes,
You
sir.
have, yeah. You have your Schrodinger equation. You have your Schrodinger equation. Let me write down. So minus h cross square by 2m del square plus v r operating on psi r will be equal to e psi r, right? This is your Schrodinger equation. And Vr, which is the potential, is nothing but minus k upon r, right? Because if you have a let's say positive proton and an electron is moving around it, and the distance between them is r, so then here it is if the nucleus will have z into e positive charge, here it will be minus e. So what
Sir,
will be
what
the
will
potential?
be
Sir,
minus?
screen not visible, sir. What you are writing not visible.
Oh, sorry. Let me. Okay, thank you. Visible now?
Yes, sir, visible.
Yeah. Yeah. So this is my Schrodinger equation, right? Three-dimensional Schrodinger equation. Minus s square by 2m del square plus Vr operating on psi r will be equal to e psi r, right? Time independent Schrodinger equation. Okay. And for hydrogen atom, Vr will be equal to minus k upon r, right? How is that it is coming? You have a nucleus and an electron. Electron is revolving around the nucleus, right? So if we take the simplest approach, it will be Coulombic potential, right? It will be Coulombic potential. So it is more like you have one charge plus Zd, another is minus E, separated by a distance R. So what is the potential? Vr is equal to how much? 1 by 4 pi epsilon naught. All of you remember?
Yes, sir.
Yeah. So that is like I'm taking that constant 1 by 4 pi epsilon naught Jd square by minus. Of course, we will have one minus over here upon r, right? So that will be equal to minus k upon r. Okay. So
Yes.
if we and this del square, if it does not depend upon if it all of you can look into the mathematical physics one that in spherical polar coordinate system, how does it look like? Okay, so if we substitute that, we can solve the that is what you will be solving in hydrogen atom actually. So you will have bunch of partial differential equations to solve. Okay, so the idea here is that if I know the potential under which the particle is interacting, then and if I have this v x1, so the potential for x1, I can solve this Schrodinger equation, time independent Schrodinger equation, to get psi 1, which is the eigenstate. And then similarly for particle 2, if I know vx2, I can solve the Schrodinger equation, time independent Schrodinger equation for the second particle, and I will get psi 2. So psi 1, psi 2 I get, and then the time evolution will be exponential minus IET by h cross. And if I write E as E1 plus E2, then simply this E1 plus E2 over here will become product here. So it will be psi 1 exponential minus I E1 t by h cross into psi 2 exponential minus I E2 by h cross. Is it clear up to this point?
Okay, sir.
So
Yes, sir.
see, so the idea is that we have two distinguishable particles and we can solve our Schrodinger equation, and to get first the time independent eigenstate and eigenvalues, and then we get the time dependent state eigenstate. So which is basically will be telling if we know the system now, what will be the system in future at a certain point. What happens in case of interacting two particle system? So if the two particles interact, then v1 vx1 x2 will be a function of x1 minus x2, x1 minus x2. Let me write down. Let me share my screen first. Yeah. So suppose we have one positive nucleus over here, another positive nucleus over here. We have one electron revolving here, another electron revolving here. If these two nucleus or atoms are close by, and then what will happen? These two electrons will start talking with each other. So then there will be another potential term which will be between these two electrons. So that potential would depend on the difference or the distance between this electron and this electron. So they are interacting. Okay?
Yes, sir.
Yeah. So if that is the case, then what we can do, we'll try to reduce or try to employ some kind of mathematical technique so that we get two independent equations like this one. If we know, if we can get two independent equations like these two, 3.10a and 3.10b, life will be easy. But here they are kind of coupled, because the potential depends on x1 minus x2. So what we do, we take x1 minus x2 as a variable, which is xr, and we take another variable which is xcm, center of mass. Cm is center of mass. Xcm, the center of mass is defined as, all of us know, right? If you have two particle system, then it is m1 x1 plus m2 x2 by m1 plus m2. Summation mi xi by summation mi. This is what. This is how you find out your uh, center of mass, right?
Center of mass. Yes, sir.
Yeah. So m1 plus m2 is capital M, which is the total mass, which is the total mass. So if we use these two variables, xcm is equal to m1 x1 plus m2 x2 by m1 plus m2, and xr is equal to x1 minus x2, and then we try to rewrite this equation Hamiltonian 3.1b 12b 3.12b, we'll try to write using 3.13a and 3.13b. Okay, how does it look like? It will become h cross square by 2m pcm square plus h cross square by 2 mu pr square plus v xr. Try to look equation 3.12b and 3.14. Do you find any similarity? x1 minus x2 becomes xr, right? So the potential part is fine, isn't it? What will
It's a
be
pretty much same, sir.
yeah. So here you can see here it will be two variables because there are two independent variables x1 and x2. So the equation 3.12b will have two variables, 1 and 2. Similarly, equation 3.14 will also have two. One is center of mass, another is reduced one, r. Okay, but what we find out here is that it will be h cross square by 2m pcm square plus h cross square by 2 mu. Mu is the reduced mass, m1 m2 by m1 plus m2, plus vxr. Now here vxr does not have a term xcm. So you see it is now kind of separated. The potential is only a function of xr, it is not a function of xcm. I would suggest if quickly one writes, let me share my screen and then ask you to do. Mm. So you have, my screen is visible?
Yes, sir.
Yes, sir.
Minus h cross square by 2m p cm square So can you substitute like this? Minus h cross square by 2 m1 plus m2. M is m1 plus m2. What is PCM? PCM will be equal to MXCM. MXCM, right? MXCM square dot, of course, dot. MXCM dot square plus h cross square by 2 mu. Mu is m1 m2 by m1 plus m2 plus PR. PR is sorry, multiplying here. Wait. Mu xr, so it will be m1 m2 by m1 plus m2 xr dot square plus b XR. Clear, right?
Yes, sir.
Well, yeah. My idea is basically to find out if those two equations are same or not, because this is we are simply jumping from 3.12b to 3.14. Yeah, of course. So then, what will it be? Minus h cross square by 2 1 plus m2 m1 plus m2 square, and xcm is what? M1 x1 dot plus m2 x2 dot by m1 plus m2 square, the first term over here, plus okay, here minus 1 minus h cross square minus h cross square by 2 m1 plus m2. Then again we will have m1 up to y plus m2. XR is x1 minus x2. So x1 dot minus x2 dot whole square plus b x1 minus x2. Is it clear? Are you following this equation?
Yes, sir.
Yeah. So
Yes.
then you can do this algebra, like, try to simplify. If you simplify this equation, you should be getting 3.12b. Can one of you work it out quickly? We're kind of going in the reverse direction. We're taking this form, and where if we get equation 3.12b, then let me come to. So we are going from 3.14, this one. If we can reduce it to this one, then it is obvious, right? Otherwise, it looks like a jump from 3.12 to 3.14. Do you get it? Are you able to follow this equation over here? Is it clearly visible or not? I'm not sure.
Yes, sir.
Yeah. Maybe I can realize it so that. Okay. All right. So then you can work it out. You can work it out. If you are not able to do it, then maybe we can discuss again. But my point is that equation 3.12b with these two variable change can be written as 3.14, which is uh, part of it is in center of mass system, and other one is the reduced one. So then you can see I can simply variable separate it. One is minus h cross square by 2m PCM square psi. Another one will be minus h cross square by 2 mu PR square plus VR, because here there was no R. So then there are two separate equations. One is this one, minus h cross square by 2m this del square by del xcm square psi is equal to ECM psi. The other one is minus h square by 2 mu del square by del xr square plus Vxr. Here is the potential. Psi R would be equal to ER psi R. And total energy would be energy, central mass energy plus reduced energy. and the time evolution part would be simple, right? Because that will be uh, IET, so exponential minus ICMT by h cross exponential minus IERT by h cross. Okay. Okay, at this point, I'll take a couple of minutes break. In this break, I would suggest all of you to look at these equations once again. If you are not following any part of it, we can discuss. Okay, couple of minutes break. So, any questions up to this point?
सर इसमें टोटल कितने यूनिट्स आएगा?
मटेरियल नहीं मिला है आपको?
सर मेरे पास नहीं है.
Okay, then maybe after the class I can share there are two PDFs actually.
Okay, sir. How many units?
I think 7 units.
Okay, sir.
Yeah.
Actually, all 4 units have been, blocks are added in the e-GAN course. Today,
Yeah, you will find it. You will find all the materials for
Yeah.
all papers in e-GAN course. Okay.
Earlier 2 were
Maybe
there, now another 2 has been added. All 4 blocks of advanced quantum mechanics are available.
Yeah.
Actually, sir, whenever we went through the courseware, this step jumping is making some difficulty because now you are referencing, then you can catch up. But when we are in silo, it's become little difficult.
Yeah, the other difficulty is, I guess, yeah, it's my guess actually that you have not completely been covered on quantum one,
Those are the issues. Yes.
because
Unless, uh,
once you are very much familiar with quantum one, whatever is discussed in quantum one, then it will be much easier. You will catch up the step. That will not be an issue. Uh,
mathematical method and quantum are the prerequisites for this course, right, sir?
yes, yes. Otherwise it would be, I mean, every time you have to go back, and as I said, I'll possibly mention, like, if you know variable separation method in partial differential equation, then this is very simple. There is nothing much actually.
That's simple mathematics.
Yeah. So in the first case, actually, we choose two completely distinguishable particles and non-interacting. So non-interacting means their potential can be separated. Once their potential is separated, then we have to actually, instead of one differential equation, we have two differential equations. And we solve it, we get two energies, U1 and A2, which will add up to give the total energy. And the wave function will be a product of the two wave functions for particle 1 and particle 2. Whereas in second case, if they are interacting, then the potential will depend on the distance between, or the relative distance between the two particles. And in that case, we can convert it or reduce it into another set of two differential equations. One is center of mass system, another is reduced mass system. Then again, then the equations, reduced equations, are very much familiar. So the first differential equation for center of mass is like a free particle. There is no potential. And for the second one, in the reduced mass system, we know what is the potential. So once we know what is the potential, we can solve. It is more like solving time independent Schrodinger equation. So that should be fine.
Sir, one request, other than the mathematical interpretation, whenever it is possible, if you can give some highlights about how it's, affecting in our real life. Then it will be, I think, material-wise, it will be easier to written by us, because
Okay.
because so many courses there, it become difficulty for everyone as we are progressing. So, so if it is possible, I know it is very
Yeah,
absolutely.
because this, yes, quantum mechanics.
Uh,
I would suggest all of you, if you find those who are interested, okay, those who are interested to go a little bit deep in quantum mechanics, so then read a book by quantum mechanics by J.J. Sakurai. J.J. Sakurai.
is
So
it Japanese, sir? Japanese person.
Sakurai, maybe Japanese. Yeah, I think it is Japanese. Uh, there you will find completely different formalism of quantum mechanics. So after this quantum 1 and quantum 2 course is over, you are done and dusted with the exam and everything. If somebody is interested, read that book. You will enjoy it, because then there is different kind of mathematics you will see. Okay, here we are, everything is coming from classical to quantum, but then Sakurin, as per Sakurai, we cannot come from classical to quantum. It is completely, paradigm shift. Thinking levels are different in quantum mechanics. So yeah, because in quantum mechanics there are few things. As you can see in quantum one also, we started with some kind of mathematical building blocks, axioms or assumptions, right?
Mm, mm.
And then we are developing the mathematics, and if the end result is something matching with the experimental one or the detected one, then that is fine, right? Because classical physics is not able to explain stuff in the phenomena in the quantum regime. So we need to develop some mathematics, and we develop the mathematics based on some axioms or some assumptions, right? So that is basically how. So mathematics wise, it will be. I don't know how far I can give you day-to-day life examples, but I'll
Actually,
try. Yeah.
it is very difficult. We all know, but
For
still,
example, this once you understand this quantum one and quantum two, then when you go to, let's say, solid state physics or condensed matter physics, then you will understand it better, because this, the application of this stuff will be there in condensed matter physics. But so then that time it will be easier to give day-to-day life examples. But I don't know. Right now, we'll see.
sir, there is a reason. It's actually many of us are going for second. I mean, second year. That is third semester.
Yeah.
Now, third and fourth, we have some optional papers. Now it is difficult to identify what exactly we are looking, or what should it go, or what kind of materials we are going to get. So that kind of decision is also, I mean, a little as because we need to fill up the form by next 1 month. So that is
Yeah,
another issue.
I would suggest at least go through quantum one, quantum two, electrodynamics. Then you will be, and electronics. Then you will be able to judge like what exactly you are interested in, because some.
And there is no actually no support in electronics paper. They have provided some way, I mean, link. So link is okay, but again, I think the future batch, that paper should be corroborated. I think that will be helpful for the students, learners.
Yeah, but some books must have been prescribed, right?
No, they have just given some links that you. There are some, I mean, tutorials, YouTube
Okay.
links that they have been provided. So there is no, I mean, study material for electronics paper.
Okay, that might be under development now.
हाँ थोड़ा अगर फीडबैक आप लोग थोड़ा दे देते हैं आप, बिकॉज यू आर द, बट इन एनी केस Bhubaneswar region is doing a fantastic job for us. We salute your commitment of whole team. Sometimes
Yeah,
we,
we'll,
we
we'll
rather lag behind. That is our problem. But kudos to you, sirs. Thank you, sir.
so should we move on to the next section?
Yes, sir.
Yes, sir. Carry on.
Yeah. So next is identicality versus indistinguishability. This is where many will have problem. Have problem in the sense, uh, what is indistinguishable? It should be identical, right? I mean, imagine you will have five glasses, same size, shape, mass, color, everything. Okay. Or glass plates. Let's say plates. I take in day-to-day life example. I have five plates. When you go to buy a crockery set or a dining set, so you have six plates. So that time, are you able to distinguish? मान लो आपके पास 6 प्लेट हैं, खाने के 6 प्लेट हैं, है ना? और सब शेप सेम है, मास सेम है, सब कुछ सेम है. आर यू एबल टू
No, sir. We will
distinguish?
not be able to distinguish.
You will be able to distinguish. Let me tell you how. Let's say you have 6 plates, right? One plate you have kept in, let's say, the table. Second plate under the table. Third plate in the kitchen. Okay. Uh, Fourth plate somewhere like on the study table or something like that. That way you will be able to identify, right?
Yes.
Yes. But that is not possible. That is possible in classical physics. So even if they're identical, but still we can distinguish. Okay, still we can distinguish. Uh, हम ये बोलते हैं कि टेबल के ऊपर जो प्लेट है वो ले आओ, या सो वी आर असाइनिंग सम ऑपरेटर पोजीशन या मोमेंटम जो प्लेट कुछ गिर रहा है या वो लाइक दैट. सो we can still assign observables to the particle, identical particles, to distinguish them. Okay, that is possible. But once we are in quantum mechanics, like electrons or photons or protons, like those kind of cases, it will not be possible to assign, because in quantum mechanics, once the problem with quantum mechanics, once we focus where the particle is, then we cannot track its trajectory. मोमेंटम के बारे में अब उस कितने वेलोसिटी में जा रहा है वो नहीं हम बता सकते, है ना.
So, sir, it is like that. Frame of reference not applicable for quantum mechanics.
No, frame of reference is applicable. Frame of reference is applicable. The problem is,
sir, are you talking about uncertainty principle?
Yes.
Okay.
So we cannot. In quantum mechanics, once if we can measure one position, we cannot know its momentum for sure, right? So unless we know its momentum for sure, then we cannot really know its trajectory, the path, where exactly it is going, right? So that is the main reason that even though in classical physics, even it is particles are identical, we possibly can assign some kind of observable to distinguish them. But in quantum mechanics, we cannot distinguish them. Those are indistinguishable. So identicality does not mean indistinguishability. So in quantum mechanics, because we are not able to, so it is written over here. You can page number 82. Two particles are said to be identical if they are exactly same in all their intrinsic properties. We could be talking about their mass, charge, or spin. The particles are exact replicas of each other. For example, like two electrons, two pions, and so on. So there can be no experiment that detects any difference in their intrinsic property. Remember, the position and the location of the particle is not its intrinsic property. Positions are not intrinsic. So even when the experiment is not one that measures one of these intrinsic properties, a system of two identical particles cannot be treated as same as system of two distinguishable particles, and vice versa. So we cannot, in case of quantum mechanics, we cannot distinguish them. So distinguishability and identicality, in it looks from normal thinking, it looks, if 6 प्लेट है सब सेम दिख रहा है, सब ऑलमोस्ट आइडेंटिकल है, तो फिर डिस्टिंग्विश करना डिफिकल्ट है. नहीं, फिर हम उसको उसका पोजीशन या उसके मोमेंटम से हम उसको डिस्टिंग्विश कर सकते हैं. लेकिन अगर क्वांटम मैकेनिक्स में है तो हम उसको डिस्टिंग्विश करना डिफिकल्ट है. वी कैन नॉट, बिकॉज क्योंकि हम पोजीशन, अगर एक बार पार्टिकल को डिटेक्ट किया तो उसका ट्रैक हम डिटेक्ट नहीं कर पाएंगे. ट्रैक को डिटेक्ट कर रहे हैं तो कौन सा पार्टिकल है वो डिटेक्ट नहीं कर पाएंगे, है ना. So that is why I guess this would be teaching this in quantum 1 actually, while expressing your linear combination. आइगन स्टेट और लीनियर कॉम्बिनेशन ऑफ आइगन स्टेट्स के बारे में बताया है क्वांटम 1 में? नहीं बताया है.
नो सर.
तो एक मैं बहुत बेसिक चीज बता रहा हूँ. ये क्वांटम मैकेनिक्स में जब आपको पढ़ाया जा रहा है कि मान लो बेसिस जो है, बेसिस स्टेट वेक्टर्स है, 5 बेसिस वेक्टर्स है या 10 बेसिस वेक्टर्स है या n बेसिस वेक्टर्स है ना? तो जो वेव फंक्शन है इट विल बी समेशन ci psi I, right? Where psi I is a eigenstate or a basis state, isn't it? मैं लिखता हूँ, लिखने से शायद आप लोगों को पता चलेगा क्या बोल रहा हूँ. So psi will be equal to C1 psi 1 plus C2 psi 2, C3 psi 3 up to Cn psi n, or I can write summation over I from 1 to n Ci psi I. ये लिखा है ना? ये
Yes, sir.
क्वांटम
Yes,
वन
sir.
में ये पढ़ा है, राइट?
What we know, sir?
या सो व्हाट इज दिस? ये क्या है? अगर इसको हम समझने की कोशिश करें तो ये क्या है? साई आई क्या है? व्हाट इज साई आई?
Well,
It's some kind of eigenstate, right? So any state of the wave function or system, any state of the system can be expressed as a linear combination of all eigenstates, right? इसीलिए तो हम लोग eigenstates के पीछे पड़े हैं ना, एनर्जी eigenstates. एक बार एनर्जी eigenstates मिल गया, सारे एनर्जी eigenstates मिल गया, तो हम उस मान लो किसी के 3 eigenstates है, किसी के 5 eigenstates है, 10 eigenstates है, 10 eigenstates मिल गए तो उसका लीनियर कॉम्बिनेशन बना के हम पूरा सिस्टम को एक्सप्रेस कर सकते हैं, है ना? तो लीनियर कॉम्बिनेशन क्यों बनाना है? Why should we be interested in linear combination? ये क्वेश्चन पूछने वाला क्वेश्चन है ना? मैं एक नॉर्मल एग्जांपल बता रहा हूँ. मान लो दो स्टूडेंट्स हैं क्लास में, स्टूडेंट 1 एंड स्टूडेंट 2, ठीक है? स्टूडेंट 1 एक पर्टिकुलर क्लास से घर से स्कूल को आ रहा है, स्टूडेंट 2 वो भी अपने घर से स्कूल को आ रहा है. तो लेट्स से वो लोग घर से जब शुरू है t इज इक्वल टू 0 और t इक्वल टू 5 सेकंड के बाद, 10 सेकंड के बाद अगर मैं दोनों को डिटेक्ट करना चाह रहा हूं तो इंडिपेंडेंटली डिटेक्ट करूंगा, राइट? स्टूडेंट 1 कहाँ है और स्टूडेंट 2 कहाँ है, ठीक है? या फिर बोलूंगा कि नहीं, दोनों का कॉम्बिनेशन इसका आधा उसका आधा लेके बोलूंगा, वो नहीं है ना? Whereas in quantum mechanics हम क्या कर रहे हैं? We take a linear combination of the eigenstates. वो कैसे आ रहा है? वही बात हम अभी डिस्कस कर रहे हैं, क्लासिकल पिक्चर एंड क्वांटम पिक्चर, ठीक है? तो क्लासिकल पिक्चर में क्या है? वो शुरू में लुक एट द डायग्राम्स है, टेक्स्ट तो पढ़ लेंगे बाद में. वो R0 और R0 प्राइम इनिशियल, आफ्टर टाइम t R0 जहां जो पार्टिकल था, पार्टिकल 1 वो कहां पहुंचा है? R में. और पार्टिकल 2 जो R0 प्राइम में था वो R प्राइम में पहुंचा है. ऑलराइट, ठीक है? क्वांटम में क्या हो रहा है? क्वांटम में क्या हो रहा है? दो पार्टिकल आ रहे हैं, यहां पे कोलाइड किया, फिगर 3.2 में कोलाइड किया, फिर कोलाइड करने के बाद वो स्कैटर हो रहा है, ठीक है? ये डायग्राम दिख रहा है ना? सो शुड आई मैग्नीफाई इट, क्योंकि ये समझना बहुत इंपॉर्टेंट है. लेट मी मैग्नीफाई लिटिल बिट सो दैट इट विल बी दिस वन. क्लियर? दो पार्टिकल्स ऑपोजिट डायरेक्शन से अप्रोच कर रहे हैं, फिर कोलाइड हुआ, यहाँ पे कोलाइड होने के बाद वो लोग स्कैटर होंगे, ठीक है? और मैंने यहाँ पे एक डिटेक्टर सेट करके रखा हुआ है. ऑलराइट, आई सेट अ डिटेक्टर ओवर हियर and I detected one particle. ठीक है, तो वो पार्टिकल, ये वाला पार्टिकल, अगर मैं इसको 1 बोल रहा हूँ, ये पार्टिकल ऐसे स्कैटर होके यहाँ पे गया है, या फिर ये पार्टिकल यहाँ से स्कैटर होके ऐसे गया है, तो पता चलेगा क्या? नहीं चलेगा।
No, sir.
है ना? So here I would not know whether this particle has gone to this detector or this particle has gone to this detector. तो इसके स्टेट और इसके स्टेट में कौन सा स्टेट वहां पे गया? सो इट हैज टू बी अ लीनियर कॉम्बिनेशन। अगर एब्सोल्युटली पता होता तो मैं क्या करता? अगर एब्सोल्युटली पता होता, so then I could have just written like state function. हाँ, so इसीलिए क्वांटम मैकेनिक्स में हम क्या कर रहे हैं, जैसे इस वाले पिक्चर में देखोगे, इनिशियल से फाइनल गया है, इनिशियल से फाइनल गया है, आइदर ये स्टेट होगा या फिर ये स्टेट होगा। बट क्वांटम में क्या है? इट विल बी अ लीनियर कॉम्बिनेशन, इट विल बी अ लीनियर कॉम्बिनेशन। मेन रीजन क्या है? once we know the particle, once we are detecting the particle position of the particle, we cannot detect its trajectory. हम उसका ट्रैजेक्टरी बता नहीं सकते हैं एब्सोल्युटली। So it has to be a linear combination. तो इसीलिए क्या है, जो जैसे आपको क्वांटम 1 में पढ़ाया गया होगा, ये जो समेशन सी आईज है, ये बेसिकली फ्रैक्शंस है। ये सी आईज जो है वही फ्रैक्शंस है, राइट? समेशन सी आई स्क्वायर जो होता है वो दैट विल बी इक्वल टू 1। समेशन सी आई स्क्वायर विल बी इक्वल टू 1। नॉर्मलाइज्ड कंडीशन होता है ना? क्योंकि ये वो फंक्शन भी तो नॉर्मलाइज होना है ना, ये ऑलरेडी आइगन वेक्टर्स जो हैं वो नॉर्मलाइज होते हैं। तो अगर एनी वेव फंक्शन हम ले रहे हैं उसको भी नॉर्मलाइज करना है, तो द कंडीशन हैज टू बी समेशन ओवर आई सी आई मॉड स्क्वायर विल बी इक्वल टू 1। ठीक है, ये चीज थोड़ा आप लोग जो क्वांटम 1 में भी पढ़ाया होगा या पढ़ाएंगे।
Sir, they are just like probabilities.
Yes, probabilities, but that's what I'm saying कि probability में जाना क्यों है? प्रॉब्लम यहाँ पे यही आ रहा है, हमें मान लो दो पार्टिकल हैं, जो पार्टिकल हम डिस्टिंग्विश नहीं कर पा रहे हैं, तो अगर उसका स्टेट को एक्सप्लेन करना है तो कैसे करेंगे? ये भी हो सकता है, वो भी हो सकता है। सो वी हैव टू टेक ए लीनियर कॉम्बिनेशन। वो तो बाद में हम बता रहे हैं कि वो जो समेशन जो सी आई मॉड स्क्वायर होगा वो बेसिकली प्रोबेबिलिटी ऑफ फाइंडिंग द पार्टिकल इन स्टेट 1 और स्टेट 2 और स्टेट 3 लाइक दैट, राइट? सो यू आर टॉकिंग C1 mod square will be the probability of finding the particle in psi 1. C2 mod square will be the probability of finding the particle in psi 2, right? That is fine. That is coming from where? That is coming from psi mod must be equal to 1, right? ये कंडीशन होगा तभी जाके समेशन ओवर सी आई मॉड स्क्वायर विल बी इक्वल टू 1, है ना? Yeah, I think ये this part must be referred to quantum 1 जो भी पढ़ाया गया होगा, तो उससे रिलेट करेंगे तो फिर समझ में आएगा। जो मैथमेटिक्स वहां पे बताया गया है, फिजिक्स यहाँ बताया जा रहा है। डिस्टिंग्विशेबल अगर क्लासिकल सिस्टम होगा तो क्लासिकल सिस्टम में वी वुड नो कि आइदर ये वाला सिचुएशन है कि मतलब जो ये वाला पार्टिकल यहीं गया है, ये वाला पार्टिकल यहाँ गया है, नहीं तो दूसरा सिचुएशन है कि ये ऐसे रिवर्स गया है, ये ऐसे रिवर्स होके यहाँ गया है। बट क्वांटम में हमें पता नहीं, ये ट्रैजेक्टरीज हम क्वांटम में नहीं बता सकते हैं। अगर ये ट्रैजेक्टरीज पता नहीं है तो हम नहीं बोल सकते कि ये पार्टिकल यहाँ गया है या पार्टिकल 1 पी में डिटेक्टर में गया है या पार्टिकल 2 डिटेक्टर में गया है। ट्रैजेक्टरी अगर पता चल रहा है तो हम बता सकते हैं डिस्टिंग्विशेबल है, इसमें हम बता सकते हैं। क्लासिकल सिस्टम में इनिशियल टू फाइनल ऐसे गया है, डायरेक्ट गया है या क्रॉस होके गया है। बट in case of quantum we cannot really tell. In case of quantum we cannot tell that. We have to take a linear combination. Clear? ये थोड़ा डाउट आ रहा है।
No, sir, clear.
Yeah. Next is exchange degeneracy. एक्सचेंज डिजेनरेसी क्या है कि अगर हम सिस्टम जो भी टू पार्टिकल सिस्टम ले रहे हैं उसका एनर्जी निकाल रहे हैं, एनर्जी आइगन स्टेट्स से एनर्जी वैल्यू ऑफ एनर्जी जैसे हमने पहले निकाला E1 E2 करके, बट अगर पार्टिकल इज इनडिस्टिंग्विशेबल है, पार्टिकल को हम डिस्टिंग्विश नहीं कर पा रहे हैं, तो 1 को 2 कर दिया, 2 को 1 कर दिया, फिर भी तो वही एनर्जी आएगा, है ना, क्योंकि पता तो नहीं चल रहा है. We are not able to distinguish whether this particle 1 or particle 2. So in that case, we can simply flip it. I would say flip. Take particle 1 जो बोला था उसको particle 2 कर दो, particle 2 जिसको बोल रहे थे particle 1 कर दो. तो एक नेचुरल क्वेश्चन आएगा कि सर हम तो उसको डिस्टिंग्विश नहीं कर सकते, तो 1 2 कैसे अटैच करेंगे? वो तो उसका सॉल्यूशन ये मतलब उसको कैसे समझेंगे कि ऑब्वियसली हम उसको डिस्टिंग्विश नहीं कर सकते हैं, इसीलिए हम बोल रहे हैं कि 1 जो पार्टिकल 1 है वो पार्टिकल 2 भी हो सकता है, और जो पार्टिकल 2 है वो पार्टिकल 1 भी हो सकता है. सो इन दैट केस अगर हम देखें तो देयर विल बी टू स्टेट्स and those will be having same energy. So this kind of degeneracy, जो रिपीटेशन हो रहा है, सेम एनर्जी पे दो स्टेट हो सकते हैं या तीन स्टेट हो सकते हैं, now depending on दो पार्टिकल है तो दो स्टेट्स होंगे, मोर देन टू है तो विल टेक ए परम्यूटेशन, राइट. तो उस केस में that kind of degeneracy is called exchange degeneracy. That kind of degeneracy, so it is written here, if particles are identical, then psi p1 and psi p prime 2. So this is attaching first particle 1, second particle 2, and psi p prime 1 and psi p2 are not distinguishable, although they are different. Suppose you make a measurement on the two particle system, and the result of the measurement may give you P and P prime, but you would not be able to say whether the final state of the system was psi p1 psi p1 and psi p prime 2 or psi p prime 1 or psi p2. मतलब फिर एक्सचेंज हुआ है या नहीं हुआ है हम नहीं बता सकते हैं. It would therefore be correct to say the final state is a linear combination of the two states. तो इसलिए बेटर यही है कि ये भी हो सकता है, ये भी हो सकता है, so we'll take a linear combination. So this is the reason why we are taking a linear combination all the time in case of quantum mechanics. एंड उसकी वजह से जो डिजेनरेसी आ रहा है, एनर्जी सेम एनर्जी होगा बट दो डिफरेंट स्टेट्स हैं, तो उसके लिए उस काइंड ऑफ डिजेनरेसी को वी कॉल इट एक्सचेंज डिजेनरेसी. एनी क्वेश्चंस? सर no. Okay, then we move over to something called symmetric and antisymmetric states. Symmetric states and antisymmetric states. तो क्या है symmetric states and antisymmetric states? Let us come to these two equations first. No, not that one. Over here. 3.19. क्या बोल रहे हैं? This is the probability of finding. क्या है ये? What is this? दो indistinguishable particles हैं, है ना? Let us read it first. Let us say that two particle wave function for a system of two identical particles in one dimension will be psi x1 x2 t. For our discussion in section this one, we know that for particle 1 at x1 and particle 2 at x2 is quite indistinguishable. अगर two identical indistinguishable particles है तो हम psi x1 x2 t लिख सकते हैं. psi x1 x2 t mod square d x1 x2, ये क्या है? Probability of finding the particle at particle 1 at x1, particle 2 at x2. yes, क्योंकि वो indistinguishable है, it is same as probability of finding the particle 1 at x2 and 2 at x1. So these two are quite same. अगर ये same है तो psi x1 x2 t mod square over here must be equal to psi x2 x1 t mod square. मतलब अगर हम उसका पोजीशन चेंज कर रहे हैं, दो इलेक्ट्रॉन है, इलेक्ट्रॉन 1 जो है वो r1 पे है, इलेक्ट्रॉन 2 जो है वो r2 पे है, अगर उसको हम चेंज कर देंगे कि इलेक्ट्रॉन 2 r1 पे है और इलेक्ट्रॉन 1 r2 पे है, तो भी हम उसको पता नहीं कर पाएंगे, क्योंकि प्रोबेबिलिटी जो है, जो प्रोबेबिलिटी है वो सेम दिखाएगा, which is mod square. अगर ये psi x1 x2 t mod square is equal to psi x2 x1 t mod square, तो क्या होगा? When is it possible? अगर एक फेज फैक्टर e to the power I थीटा रहेगा, अगर एक फेज फैक्टर e to the power I थीटा रहेगा, तो इसको अगर लेफ्ट साइड को हम स्क्वायर करेंगे, राइट साइड को स्क्वायर करेंगे, तो क्या होगा? e to the power I थीटा into e to the power minus I थीटा will become 1. So psi x1 x2 t mod square will be equal to psi x2 x1 t mod square. All right. So अगर e to the power I theta उस केस में लेंगे तो e to the power I 2I theta will be equal to 1. So theta will be equal to 0 and pi. So that is giving rise to basically, ये quite obvious है, that psi x1 x2 t will be either equal to psi x1 x2 t or it will be minus. So if it is plus then it is symmetry. मतलब फ्लिप करेंगे, अगर पार्टिकल्स अपना पोजीशन चेंज कर रहे हैं फिर भी वेव फंक्शन चेंज नहीं हो रहा है, तो सिमेट्रिक स्टेट है. और अगर पार्टिकल पोजीशन चेंज करने से वेव फंक्शन इज जस्ट बिकमिंग नेगेटिव ऑफ द ओरिजिनल वन, देन इट इज कॉल्ड एंटीसिमेट्रिक. बट डिटेक्ट करते टाइम इट इज वेरी मच इंपॉर्टेंट. यहाँ हम वेव फंक्शन की बात कर रहे हैं, जब हम डिटेक्ट करेंगे तो वो साई मॉड स्क्वायर होगा, तो डिटेक्शन में हमको पता नहीं चलेगा. Only in the wave function we can make the change. Obviously, we will see the effects in other measurements. अगर कुछ other measurements कर रहे हैं जहाँ पे only psi के ऊपर ऑपरेशन होगा ऑपरेटर, तब हमें पता चलेगा. बट अगर सिर्फ probability of finding the particle हम निकालने की कोशिश कर रहे हैं, if we are trying to find out what is the probability of finding the particle at x1 and x2, then we will not see any change, because the first one will be psi x1 x2 mod square, second one will be psi x2 x1 mod square, both will be equal to, both be same. But if we go back to the wave function, then it will be psi x2 x1 t will be equal to psi x1 x2 t then for symmetric case, and minus of psi x1 x2 t in case of antisymmetric case. समझ में आ रहा है सिमेट्रिक स्टेट क्या है, एंटीसिमेट्रिक स्टेट क्या है?
Yes, sir.
Right. Then we go back to permutation operator. Permutation क्या है? Combination, मतलब अगर more than one है तो हम उसका क्या कर सकते हैं? जैसे मान लो नंबर असाइन करके, ये शायद +2 वगैरह में आप लोगों ने थोड़ा बहुत किया होगा permutation.
But sir, in a permutation, the order is important.
Yes,
Combination
here
is not
here
important.
here we will see. Here permutation में order important है, combination में order नहीं होता है, right?
Yes, sir.
Yeah, but in this case also, in this case हम लोग permutation की बात कर रहे हैं, क्योंकि particle 1 permutation कहाँ होता है, वो और एक चीज भी ध्यान रखना है. permutation कहाँ होता है? जहाँ पे distinguishable है ना?
Yes, sir.
combination कहाँ होता है? जहाँ पे distinguishable नहीं है, क्योंकि पता नहीं चलेगा कि order important, order नहीं है, तो ऑर्डर नहीं, मतलब वो डिस्टिंग्विशेबल नहीं है ना?
Yes, sir.
तो परम्यूटेशन हो रहा है, मतलब हमें पता चल रहा है कि जो इलेक्ट्रॉन 1 कहाँ पे है, इलेक्ट्रॉन 2 कहाँ पे है ना? तो ये सिचुएशन ऐसा है कि हम पहले उसको बता रहे हैं कि मान लो हमें पता चल रहा है कि वो हम डिस्टिंग्विश कर पा रहे हैं, तो सिचुएशन क्या होगा, तो फिर बाद में हम उसको बोलेंगे कि अगर डिस्टिंग्विश नहीं कर पाए तो फिर क्या सिचुएशन है ना? So P12, let me come to the equation, then you will be able to understand. P12 operator, okay? We define a permutation operator P12. ये किसके ऊपर ऑपरेट कर रहा है? psi P1 and psi P prime 2. That will give psi P prime 1 and psi p2. तो ये p12 ऑपरेटर क्या कर रहे हैं? इट विल सिंपली वेव फंक्शन जो फर्स्ट इलेक्ट्रॉन का एट पोजीशन 1 सेकेंड इलेक्ट्रॉन का एट पोजीशन 2 था उसको फ्लिप कर देगा. सेकेंड इलेक्ट्रॉन को पोजीशन 1 पे ले आएगा, फर्स्ट इलेक्ट्रॉन को पोजीशन 2 पे ले जाएगा. दिस इज हाउ वी आर डिफाइनिंग द परम्यूटेशन ऑपरेटर p12. ठीक है. So what will be p12 square? It has to be identity, right? p12 square has to be identity, right? क्योंकि एक बार फ्लिप किया, अब दोबारा उसको फिर से फ्लिप किया तो वो ओरिजिनल स्टेट में चला जाएगा, isn't it? All of you following this one or not?
Yes, sir.
Yeah. So then p12 square will be equal to identity. If p12 square is equal to identity, then obviously p12 will be equal to p12 inverse. Somewhere it must be written p12. Yeah, here p12 must be equal to p12 inverse, right? Now the most interesting part will be the what will happen to an observable. What will happen to an observable? So that's what it is telling. Let us now say that the states psi p and psi p prime are the eigengates of a single observable O for the particle. वो एनर्जी हो सकता है, मोमेंटम हो सकता है. बोल रहे हैं कि psi p and psi p prime are the eigengates of a single observable O of the particle, where psi p and psi p prime are orthogonal and normalized. Because they are separate, two different ones. If O1 is the operator corresponding to observable O for particle 1 and O2 is the operator corresponding to O for particle 2, you can instead of O you can take, let's say, energy H1 and H2. So total observable is H energy. So for the first one it will be H1, for the second one it will be H2. So instead for a general discussion, it is taken operator 1 and operator 2. So O1 operating on the state psi p1, psi p1 and psi p prime 2 will be equal to omega p psi p1. So this is like simple your eigenvalue equation, and similarly for particle operator 2 O2, this will be the equation. If that is the case, if I operate P12 now, ये जो फर्स्ट वाला इक्वेशन 3.26a है, उसके ऊपर अगर मैंने P12 ऑपरेटर ऑपरेट किया, P12, so what will it be? तो बोथ साइड P12 ऑपरेट किया तो पहले हमने डिफाइन किया था कहाँ पे, यहाँ पे psi P12 ओमेगा सॉरी P12 psi P1 psi P prime 2, तो वो फ्लिप कर देगा. तो यहाँ पे वही किया है, psi P12 O1, it will operating on this one. What will it do? It will flip it, right? It will flip it. And P12 inverse, अगर यहाँ पे P12 inverse अप्लाई करेंगे, so what exactly will P12 or P12 inverse is equal to identity. So finally you will end up with this kind of equation. P12 O1 P12 inverse is equal to O2. So this equation is nothing but if I multiply P12 inverse on the right, so that will give me a bracket, right? That will give me a bracket. P12 O1 P12 inverse is equal to O2. So this is the condition. This is the condition one has to satisfy. If it is Hamiltonian, so P12 H P12 inverse is equal to H, the same energy. So this is most important one, that the eigengates of the Hamiltonian operator are also eigengates of the permutation operator. तो मतलब अगर हमने उसको फ्लिप किया, पोजीशन फ्लिप किया, तो भी जो स्टेट निकलेगा वो एनर्जी आइगन स्टेट्स होंगे, वो एनर्जी आइगन स्टेट्स होंगे। ठीक है, and if we try to express them again in terms of symmetric and antisymmetric states, so symmetric case में क्या होगा, we have to take a plus sign over here, and in antisymmetric case we have to take a negative sign over here. So this will be antisymmetric and this will be symmetric. सिमेट्रिक एंटीसिमेट्रिक वो फॉर्मूले थोड़ा याद रखना है ना, सिर्फ ये याद रखना है कि सिमेट्रिक केस में वो प्लस होता है, लीनियर कॉम्बिनेशन में प्लस होता है, एंटीसिमेट्रिक केस में वो माइनस होता है ना। तो सिमेट्राइजेशन पोस्टुलेट क्या बोल रहा है, इट इज ऑलमोस्ट लाइक अनदर पोस्टुलेट फॉर क्वांटम मैकेनिक्स. So what we have established so far is that the two particle state can be either symmetric or antisymmetric under an exchange of particles. अगर हम p12 permutation operator operate कर रहे हैं तो either it will be symmetric or it will be antisymmetric. However, it turns out that all allowed states of a system of any number of identical particles of a particular kind must always be either be symmetric or antisymmetric under exchange of a pair of particles. मतलब मान लो हमारे पास दो इलेक्ट्रॉन है और उस या दो क्वांटम पार्टिकल है, उसको अगर हम इनडिस्टिंग्विशेबल अंडर इनडिस्टिंग्विशेबल कॉन्सेप्ट में डिस्कस कर रहे हैं तो पूरा का पूरा सिस्टम जो है वो इधर सिमेट्रिक स्टेट में एक्सप्रेस हो सकता है या एंटीसिमेट्रिक स्टेट्स में एक्सप्रेस हो सकता है. आइडेंटिकल इंडिस्टिंग्विशेबल पार्टिकल्स हैं तो हमेशा क्या होगा, क्योंकि वो इंडिस्टिंग्विशेबल है तो वो इधर इट विल बी सिमेट्रिक और एंटीसिमेट्रिक, so it will be either a plus combination or a minus combination. The symmetrization postulate stipulates the available states of many particles of the same type have to be either exclusively symmetric or exclusively antisymmetric. So there are two kind of identical particles. Those which are always found in symmetric state, जो particles हमेशा symmetric states में पाए जाते हैं, those are called bosons. And those states, particles which are always found in antisymmetric states are called fermions. इनसे पता नहीं चलता है कि सिमेट्रिक स्टेट से पता नहीं चलता है कि बोसॉन्स और फर्मियंस हैं. Later on, actually, boson name is coming from the statistics they follow. Once we want to express them as a statistical distribution, we have to use Bose-Einstein statistics. So that is why it is called boson. But all these bosons are always expressed in symmetric states, plus one. And all the fermions are actually expressed in antisymmetric or negative combination states. And it is very much, since it is, you can see, Pauli exclusion principle will be automatically coming from this one. जो एंटीसिमेट्रिक स्टेट था, यहाँ पे हमने लिखा है एंटीसिमेट्रिक, वो क्या था, n-1 psi p1 psi p prime 2 minus psi p prime 1 psi p2. This is the antisymmetric state. Now come to this case. So that normalization factor is 1 by, so वहाँ पे जो n-1 था, that will be 1 by root 2. Psi p prime minus psi p prime psi p. If now we assert that the two single fermion states are identical, अगर हम बोल रहे हैं कि दो fermion states identical है, तो मतलब p और p prime same है, तो p और p prime same होंगे, तो ये क्या हो जाएगा, psi p, यहाँ पे भी होगा psi p, so that will be equal to 0. That means there will not be any state where two fermions will be in the same identical states. यही तो पाउली एक्सक्लूजन प्रिंसिपल है कि कोई भी दो इलेक्ट्रॉन लिया, जो दो फर्मियंस लिया, वो दोनों के वेव फंक्शन और इंट्रिंसिक प्रॉपर्टी सारे सेम नहीं हो सकते हैं। सेम हुआ तो क्या होगा, बिकॉज दैट इज एक्सप्रेस्ड बाय एंटीसिमेट्रिक स्टेट, वो एंटीसिमेट्रिक स्टेट एग्जिस्ट ही नहीं करता है। इज इट क्लियर?
At least spin quantum number has to be different.
यस, आई मीन इंट्रिंसिक प्रॉपर्टी में हम बोल रहे हैं कि हमें पता नहीं है कि वो स्पिन है या मास है या चार्ज है, बट वेव फंक्शन दोनों जो, क्योंकि वो किसी भी वेव फंक्शन स्टेट को एक्सप्रेस करने के लिए उसके सारे इंट्रिंसिक प्रॉपर्टी को एक्सप्लिसिटली बताना पड़ेगा, है ना। अगर मैं किसी इलेक्ट्रॉन के बारे में बता रहा हूं तो मुझे उसका पोजीशन, एनर्जी, एंगुलर मोमेंटम, स्पिन, सब कुछ बताना पड़ेगा। तो अगर हम दोनों ऐसे इलेक्ट्रॉन ले रहे हैं तो दोनों इलेक्ट्रॉन के सारे प्रॉपर्टी सेम नहीं हो सकते, क्योंकि सारे प्रॉपर्टी सेम हुए तो ये साई पी और साई पी प्राइम तो सेम हो जाएंगे ना, दे विल बी आइडेंटिकल, राइट। अगर आइडेंटिकल हुआ तो जो टोटल सिस्टम है दो इलेक्ट्रॉन का, उसको हम कहा किससे एक्सप्रेस करेंगे, साई से, साई कैट से। तो इस साई कैट का रिलेशन क्या है, साई कैट इज इक्वल टू 1/1/√2 साई पी प्राइम माइनस साई पी प्राइम साई पी। बट सिंस पी और पी प्राइम सेम हो जाएंगे, सो दैट विल नॉट एग्जिस्ट, दैट विल बिकम जीरो। तो ऐसा स्टेट हो नहीं सकता है जिसमें दोनों के दो इलेक्ट्रॉन के सारे क्वांटम नंबर सेम होंगे, या फिर दोनों के जो इंडिविजुअल आइगन स्टेट्स हैं वो सेम हो सकते हैं, वो नहीं होंगे। दिस इज मैथमेटिकली काइंड ऑफ प्रूविंग द पाउली एक्सक्लूजन प्रिंसिपल कि अगर हम सिस्टम एंटीसिमेट्रिक से ही एक्सप्रेस हो रहा है तो उससे हम पाउली दो फॉर्म्यूल्स सेम स्टेट में नहीं हो सकते। क्लियर? या एक्सचेंज फोर्सेस में क्या हो रहा है, इफ यू हैव आइडेंटिकल बोसॉन्स, इफ यू हैव आइडेंटिकल फॉर्म्यूल्स और डिस्टिंग्विशेबल पार्टिकल्स, ये आप यहाँ से देख सकते हैं। मेरा ये सजेशन रहेगा कि जब आप लोग इस यूनिट को पढ़ रहे हैं तो पहले तीन चीजें, जैसे मैंने लेट मी गो टू द टेक अवे फ्रॉम द चैप्टर्स जहाँ पे बताया गया था, उसको थोड़ा ध्यान में रखना है, तो फिर ये यूनिट अच्छे से समझ में आएगा। क्या था? डिराइव द जनरल सॉल्यूशन ऑफ द श्रोडिंगर इक्वेशन फॉर अ सिस्टम ऑफ टू डिस्टिंग्विशेबल, दोनों डिस्टिंग्विशेबल है, नॉन इंटरैक्टिंग, मतलब क्या, v1 को v इज इक्वल टू v1 प्लस v2, जो हमने वेरिएबल सेपरेट करके किया। सेकेंड वन, राइट द जनरल सॉल्यूशन ऑफ श्रोडिंगर इक्वेशन फॉर अ सिस्टम ऑफ n डिस्टिंग्विशेबल नॉन इंटरैक्टिंग, दो की जगह n लिया तो। फिर हम बोल रहे हैं कि अगर जनरल सॉल्यूशन ऑफ श्रोडिंगर इक्वेशन फॉर सिस्टम ऑफ टू डिस्टिंग्विशेबल एंड इंटरैक्टिंग हुआ तो क्या होगा, योर पोटेंशियल विल बिकम v will be equal to v of x1 minus x2, तो उसको हमने कैपिटल M और म्यू जैसे सेंटर ऑफ मास और रिड्यूस्ड मास कोऑर्डिनेट में उसको सॉल्व किया। डिराइव द सिमेट्रिक एंड एंटीसिमेट्रिक सॉल्यूशन फॉर सिस्टम ऑफ टू आइडेंटिकल पार्टिकल्स एंड एक्सप्लेन एक्सचेंज डिजेनरेसी। हमने देखा कि एक्सचेंज डिजेनरेसी होके कैसे हो रहा है, पार्टिकल अगर पोजीशंस या उसको हम चेंज कर पार्टिकल 1 पार्टिकल 2 ऐसे करके कर रहे हैं। And permutation operator on a quantum state of identical particles, and how exactly we are getting Pauli exclusion principle out of this discussion. Last one is apply the method of canonical quantization. Canonical quantization क्या है? ये basically going from classical to quantum, classical formalism to quantum formalism. क्लासिकल मैकेनिक्स में हैमिल्टन थियरी पढ़ा चुके हैं?
Yes, sir.
Yes, sir.
सो वहां पे आप लोग, लेट मी कम टू द इक्वेशन, then it will be familiar to you. You're familiar with this one, right? Poisson's bracket?
Yes, sir.
Yeah. So Poisson's bracket is basically moving over to commutator bracket in quantum mechanics. Okay. Poisson's bracket, ये आप लोग क्लासिकल फिजिक्स में पढ़े होंगे. टाइम वेरिएशन of a dynamical variable or time evolution of a dynamical variable.
Yes,
Del
sir.
O by del T is equal to OH Poisson bracket where H is the Hamiltonian, right? तो क्वांटम में हम क्या कर रहे हैं, सिर्फ Poisson bracket को we are moving it to commutator bracket. ठीक है?
Yes, sir.
Yeah. So this kind of formalism, और उससे हमें क्या हो रहा है, हमारे सारे जो जितने डिस्कशंस हैं क्वांटम में वो सही बैठ रहा है. कहीं से तो हम क्लू लेके चलेंगे ना. So this is the one we are taking. So this is like canonical momentum, canonical coordinates and canonical momentum जो है, उसी को हम ऑपरेटर फॉर्मलिज्म में लेके फिर योर जो canonical ब्रैकेट है Poisson's ब्रैकेट, उसको हम कन्वर्ट कर रहे हैं कम्यूटेटर ब्रैकेट में. Then we are moving
Sir,
from
in classical, excuse me, sir.
Yeah.
Sir told that only IH cross will be added to the Poisson bracket. So, what is the reason of that? Because of uncertainty.
In case of going from classical to quantum,
The Poisson bracket will be called commutator bracket, but IH cross term will be added.
yes,
Sir
1
has
upon
told.
IH cross. That is
Ah.
what it is telling over here. Huh? Your xi is going to xi cap. Huh? Your
They
pi
will be
is going,
operators.
and then your Poisson bracket, yes, and your Poisson bracket is going to 1 upon IH cross, your commutator bracket. No, the reason could not is not uncertainty. It is basically how we convert the formalism, from classical picture to quantum picture. ऑब्वियसली अनसर्टेनिटी तो है, इसीलिए तो हम लोग जैसे मैंने शुरू से बोला ना कि इनडिस्टिंग्विशेबल हो रहा है, तभी हम लीनियर कॉम्बिनेशन लेना जरूरी है, क्योंकि हम उसको जो पाथ है उसको हम ट्रैक नहीं कर पा रहे हैं, है ना.
Yes, sir.
सो दिस इज काइंड ऑफ ए कंपैरिजन. अगर हमें क्लासिकल इक्वेशंस पता है तो हम उसको क्वांटम इक्वेशंस में कन्वर्ट कैसे करेंगे. This is just by looking at the classical equation. अगर मान लो इलेक्ट्रॉन एक क्लासिकल पार्टिकल होता, मैं अगर उसका इक्वेशन लिख पाता तो उसको इमीडिएटली क्वांटम इक्वेशन में मैं कैसे कन्वर्ट करूंगा. सो दिस इज द फॉर्मलिज्म. Here it is not telling anything about whether it is uncertainty or not. No. Obviously, H cross.
So basically, it's just mathematics involved in
Yeah, it is.
transformation.
मान लो एक सिचुएशन ऐसे हुआ, मान लो आपको क्वांटम मैकेनिक्स पता नहीं है, किसी एक स्टूडेंट को क्वांटम मैकेनिक्स पता नहीं है, बट क्लासिकल मैकेनिक्स उसको अच्छे से आता है. ठीक है, तो वो स्टेट ऑफ द इक्वेशन जो स्टेट ऑफ द सिस्टम है उसको वो अगर लिख रहा है, अगर ही इज एबल टू राइट द हैमिल्टोनियन, तो उस केस में अगर उसको वो पार्टिकल्स क्लासिकल की जगह क्वांटम हो जाएंगे, तो उस केस में हम क्या करेंगे. सो वी विल जस्ट जो ऑब्जर्वेबल्स है उसको हम कन्वर्ट कर देंगे ऑपरेटर्स को. बट जैसे हमने क्लासिकल फिजिक्स में टाइम इवोल्यूशन कैसे निकाला था, टाइम इवोल्यूशन टाइम चेंज कैसे होगा. सो डेल बाय डेल टी ऑफ दैट variable, dynamical variable O will be equal to the Poisson bracket of O and H.
Yes, sir.
तो उस जगह हम सिंपली ये लिख देंगे तो वो क्वांटम डिस्क्रिप्शन में चला जाएगा. तो दैट विल बी ए क्वांटम मैकेनिकल इक्वेशन. तो हमें शुरू से फिर सारे चीजें शुरू से लिखने की जरूरत नहीं पड़ेगा. ठीक है,
ठीक है सर.
Yeah. So next class we will talk about addition of angular momentum. I think that is the next chapter, I guess. Yeah. Addition of angular momentum tomorrow. Huh?
Sir, right, sir.
Yeah.
Yeah, thank you, sir.
Thanks.
Thank you.
Thanks.
Thank you,
Okay,
sir.
sir. Thank you, sir.